I'm going to start recording here. It's 1:10. It is lecture 11. This is the second to last lecture, guys. The second to last lecture. Oh, man. Um, yeah, a couple announcements. Homework 7 is due tomorrow. And quiz 3 is also tomorrow. So I wrote it out for you guys on the quiz tomorrow. Make sure you know your tests. Make sure you know your tests, how to use all the tests. Make sure you know how to do the write-ups, okay? Haven't really been getting a lot of people like, sending me their write-ups and stuff. So, I mean, I just hope you guys are getting in the practice on your own, like don't just assume, like on your write-ups that like, yes, I know the answer, but like I want to know that you know the answer, right? So you got to make sure you're thorough with your write-ups. There's going to be one power series problem on there, so that's why I wrote know how to find your interval of convergence. And then I kind of tacked one question on there at the very end. It was more of like another conceptual question, sort of. Just make sure you know what power series are, right? Like, if someone were to ask you, if someone were to ask you what's a power series, like what would you say? Does anyone want to tell me? Like, does anyone want to try to?
A power series?
Yeah. What's a power series? Why does it get a different name?
It's a series that very well resembles a function.
A little more. Just
Um,
3 words. On and
interval?
yes.
Okay.
So a power series represents a function on a very specific interval, right? And that's what this interval of convergence was. It was that interval that tells us like, from here to here, the series represents the function really well, okay? But then like, outside, it's a bad representation, okay? So make sure you know, that. Okay, and that's it for the quiz. The quiz is, there's no sequences on it. It's just all straight up all series. Okay, so make sure you know your tests. Integral test, P series, DCT, LCT. In fact, there's a question where I specifically tell you to use the DCT, and then there's another question where I specifically tell you to use LCT. So you have to know how to use both. All right, AST, absolute versus conditional, ratio. Is that all of them? I think that's
Root?
all of them. I'm not going to test you guys on root.
What about
Okay.
geometric?
Oh, yeah. Okay, fine. Geometric series too. I think that's all the tests. But yeah, that's it. That's it on quiz 3. So please do well on this one. This is the last one. This is your last chance, okay? I was looking at the grades, and they're not the greatest. I mean, the one on Canvas, I think it's kind of messed up. I don't think it's showing you your true grades because there's no way some of you have like 85s or 89s. It doesn't sound right to me. But because like I have a different page of grades on an Excel spreadsheet with my own like formulas and stuff, and like everyone's at like a 50 because we haven't taken the final yet, and the final's like worth like 25%. So that's how my calculators work. So like, and some people are lower than 50s, and I'm just like, these people need to like kind of step it up here.
John, for the thing for Canvas, they don't count the final yet because it's not graded. So it excludes anything that's not graded up to now.
Right. So my guess is that like they're taking the percentage out of everything that's only inputted and excluding everything else that's not inputted, So and then so that's why your grades look higher, but in reality I don't think that's the case. So we'll figure it out. And oh yeah, speaking of which, your final is on Thursday. So the final on Thursday, it's going to cover series. It's going to cover a little bit of sequences. It's going to cover Maclaurin and Taylor series, which is what we're going to talk about today and Wednesday. Okay. Any questions before we dive right into this? No. Can you guys like give me like a thumbs up to tell me that you're there and you are ready and you're like, let's do this, John. I'm so ready for freaking more series and to get confused and to kind of cry a little.
Let's do this, John. I'm so ready to get ready.
Let's get confused.
All right. Awesome.
Awesome.
I'm excited.
Mr. John?
Yeah.
Is the final kind of like a quiz 4, basically? Like
it's like a quiz, but it's worth 25% of your grade. So the 3 quizzes. Okay, so the quiz is, if you read the syllabus, right? The 3 quizzes, I dropped the lowest one, and then the quizzes, I think they're worth like 20 or 25% of your grade, like altogether, right? But then the final itself, that thing is 25% of your grade. You get what I'm saying?
Yeah. Okay.
So please don't screw on the final, please.
We'll try not to.
Today we're gonna finish up building functions via power series, kind of like what we started talking about last class, and then hopefully I get to start Maclaurin and Taylor series, but we'll see how that goes. So, man, where should I start? Last class I introduced how to start using these series, right? So we understand what a power series is, right? It's a representation of a function on an interval, right? But now I threw out the question like, okay, now how do we get like specific functions, and how do we get the series representations of those specific functions, right? So I think I started off with this guy, 1 over 1 minus x, because it resembled our geometric series, right? If you guys remember.
Yeah.
And the trick was I just replaced a with 1 and r with x. And what we ended up getting was this series right here. And I'll just make a table here. So this is the function, is the series, and the interval of convergence is from -1 to 1. Can anyone explain why is the interval of convergence from -1 to 1? Where did I get that from?
From the denominator?
From the denominator. Can you be a little bit more explicit than that? Like, can you explain that a little bit more?
Like the function's domain?
No. This function's domain is not -1 to 1.
Isn't it after we do the ratio test, we get the absolute value? And that gives
so
us...
that's one way, right? So one way is I can do the ratio test on this, right? This becomes x to the n plus 1 over x to the n, absolute value less than 1, limit as n goes to infinity, yada, 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 right? And yeah, we can get that interval convergence, test our endpoints. But another way, I'll put dot, dot, dot. But another way we can get it is just by knowing what we know about the geometric series. We know that r cannot be greater than 1, greater than or equal to 1, right? So that's also where this interval convergence comes from, right? So it's like two justifications for like the same outcome, essentially. Does that make sense? And then I showed you guys a trick. I was like, well, what if we had another function that kind of resembled 1 over 1 minus x, right? What if I had like 1 over 1 plus x squared, something like that, right? The trick was, wait, I'm sorry. Let me do this one first. Actually, no, we can do this one. So the trick was to make it look like 1 over 1 minus x, right? To make it look like 1 over 1 minus x. So the idea is, well, I can do that by kind of rewriting this as 1 over 1 minus negative x squared, right? I'm not breaking any laws here, right? All I did was, because two negatives make a positive, right? So I'm not going to math jail, right? And with that being said, since this resembles this now, 1 over 1 minus x, I can turn it into a series. So essentially, like, what it kind of turns into is kind of almost like u substitution, where it's like, if it looks like 1 over 1 minus u, and u is a function, you can write it as u to the n. Does that make sense? Do you see what I'm saying here? In this case, like the u, that's u, negative x squared. So this would become negative x squared to the n equals 0 to infinity. And I can rewrite this as, it looks like there's an alternator times x squared. You guys still with me?
Yeah.
If I were to do the whatchamacallit, the ratio test on this one, my interval of convergence would end up being 1 to -1. I mean, -1 to 1. Oops. Sorry. So that's like one of the tricks that you can do if you had something that looked like this, right? So the next part of the section, there's a theorem, and this is what I was kind of hinting at last class. I was like, well, now that we're kind of familiar with like turning these into functions, let's start applying some calculus to these functions now, right? And what I mean by that is let's start deriving and integrating these. Like, can we use those same rules for these functions? Okay, there's a theorem. It's on page 600. This is the PDF page. It's labeled theorem 2. All right, it's labeled theorem 2, and it basically just states that you can derive and integrate power series because they technically represent functions, right? You can derive and integrate power series. And there's a really, really, really cool thing that happens. Okay, it's a thing that just happens because the way series and functions are. The radius of convergence stays the same. The radius of convergence stays the same. So let's say I had a function and I knew the series and I derived it. Well, if I knew the radius convergence of the original function, I don't have to do the ratio test again to see what the radius of convergence is. I just know what it is. I get it for free when I derive it. Do you guys get what I'm saying? So watch. If I have 1 over 1 minus x, I'm gonna keep this easy, right? What's the derivative of 1 over 1 minus x? Uh-oh. Did you guys forget how to derive? I hope not. I know it's been a long time.
Yeah.
Like a whole week or so, but do you guys remember how to
Derivative?
derive?
Yeah, no.
Yeah.
Zero.
Zero.
Oh my
Wait, not zero,
gosh.
not zero.
Oh, mi corazón.
Sorry.
Oh,
Sorry.
oh,
Okay.
that hurt. That hurt.
Ellen?
Okay.
Oh, who said LN? Oh, that
That's
hurt
Yeah,
even
integrated.
more.
relax,
Isn't it just
relax.
1 minus x to the negative second?
Oh my god.
Oh,
Like
yes,
the whole
hold
thing.
on.
Sorry.
Okay, no, I'm still all right. I'm good. It's a little elevated. This is the same thing as 1 minus x to the negative 1, which means the derivative is negative 1 minus x to the negative 2.
Said that.
Should have said it louder, man.
You were over here making sure you were alive. I couldn't say that loud.
Okay, so and then rewritten, this is negative 1 over what is it? 1 minus x quantity squared.
Wait. Wouldn't it
Oh
be
no, it's positive.
positive?
It's positive.
Yeah.
It's positive. Sorry.
By
I
chain
forgot.
rule?
Yeah, the chain rule. So the derivative of 1 over 1 minus x is 1 over 1 minus x squared. Pretty cool, right? So watch, when I have, this is, what I'm saying is, this represents this guy right here, right? From negative 1 to 1. I can derive the general term of the series like I normally would do a power rule, right? So like you see, oh, actually this is a good teaching moment right here. You see how you guys like tripped up from here to here, right? You guys forgot how to derive with the negative power rule. So what I'm saying is this guy is much more easier to derive if you think about it, right? If I treat n like a constant, because that's what n is, it's an index, right? It's a constant. Well, this is going to be n times x to the n minus 1. You see how I did that? I just used the power rule, didn't I? This guy here will represent 1 over 1 minus x squared on the same interval. On the same interval. That's what the theorem is saying, right? And it works for integration as well. If I were to integrate 1 over 1 minus x, and I don't think we know how to do that, so I won't do it. But if I were to integrate 1 over 1 minus x, wait, no, that would be ln, right? ln, whatever. But the whatchamacallit, interval convergence also stays the same. There is one catch though, and I said this to you guys last class. you must still check your endpoints. Okay? Because the theorem is very clear on this. It says that only the radius stays the same, not the interval. Okay? So it says the radius of convergence stays the same. So that distance from 0 to 1 stays the same, but we still, it does not tell you what's happening at the endpoints. Does that make any sense? Do you guys get what I'm trying to say? Right? So definitely still you want to check your endpoints. All right?
Yeah.
For time's sake, I'm not going to really do that for this example. I'm just going to move on to the other stuff I wanted to get to. All right, so why don't we look at this guy right here? Hold on. 1 over, so I just did this one, 1 over 1 plus x squared, and we said this was what? It was -1 times x squared from 0 to infinity, right?
Yeah.
On the same interval, -1 to 1. And do you guys notice anything peculiar about this function? Does this look familiar to you guys at all? No. No. We just did a derivative example, so what example?
Yeah.
What kind of example do you think?
Wait,
I'm gonna
wasn't
do
it -1 to the n?
Integration? Oh wait, no.
now? Okay, it is
Oh,
integration.
yeah.
Wait,
No, this function right here. It doesn't look familiar.
Yeah. Oh, yeah. Because like we did explain how it's like, yeah. The one we just did beforehand.
Does
Is it
anyone
like an
know?
inverse-
Does anyone know what the
inverse,
integral of 1 over 1 plus x squared is?
Isn't it like an inverse
Isn't-
trig function?
It is.
I
It
don't
is.
remember
Which
which one.
inverse trig function? Which one?
Maybe
arctan?
tan? I don't know.
Maybe tan. Okay, I'll take it. Yes, it's tan. It's tan inverse. The derivative of tan inverse is 1 over 1 plus x squared. So what are we going to try to do here? We are going to try to find the series representation of inverse tan. Sound cool? Sound good? Yes? Okay, so watch. Here's the move. I'm going to integrate both sides. Oh man, worlds colliding, right? Integrals and sums, right? So I'm going to integrate both sides. So the right side, what this is going to look like, if I were to string this out a couple of terms, I forgot my ends, whoops. If I were to string this out a couple of terms, well, my first term, it looks like 1. And then the next term is it's going to alternate and then be x squared. And then it's going to alternate x to the 4th, alternate x to the 6th, alternate x to the 8th, and so on and so forth, right? I'm just writing out the first couple terms of the series. And now I'm integrating it. This is called term-by-term integration, by the way. Hopefully it's self-explanatory what that means, right? And this side's going to come tan inverse of x. And look, this is really, really easy to integrate. This is what I was trying to say too the other day, right? Computing integrals and computing derivatives with just power functions is much more easier for a computer to do than like, you know, memorizing the derivative of sine or the integral of tan inverse. You get what I'm saying? Like I can do this in my sleep, right? I know what the integral of 1 is, or hopefully you guys know. I know what the integral of x squared is and x to the 4th and so on and so forth. You know? So this is what I mean. Like this for computers is much easier to interpret. So what are we doing now? So now we're going to integrate. Cool. Integral of 1 is x. Integral of x squared. Somebody, please
X
restore my
cubed
faith.
over 3.
Yes, negative x cubed over 3. And then x to the 5th over 5.
5.
X to the 7 over 7. Do we see a pattern? Do we have enough terms to see a pattern here? What's going on with the x's?
The power is the same number as the number in the denominator?
What else?
And there's like
They're
a
going
common
up by
ratio
2.
of 2.
They're going up by 2.
Yeah.
Another way to say this is they're all odd. right? All the powers are odd. And so there's a trick. There's a trick to this. You'll see this a lot, and I'll write it off to the side. Whenever you see like odd stuff happening, not like strange, I mean like odd, like mathematically odd things happening, you'll see this 2n plus 1. Just think of that when you see odd. Even is going to be 2n, right? Because if you have a number and you multiply it by 2, it forces it to be even. Or if you have a number, multiply it by 2 and add 1, it forces it to be odd, right? Give me any number you want. Multiply by 2, add 1, it'll be odd. Yes? Make sense?
Okay. Yeah.
Okay. So this is what we're going to do. We're going to say x to the 2n plus 1, because that means it's going to be an odd number. And so long as my index lines up with that, right? If I plug in 0 into n, I get x to the first power as my first term. You see that?
Yeah.
So that's going to follow suit. The denominator, though, the denominator has to start on 1. So what do you think we're going to do for that?
It has to start on 1.
Yeah, because like the denominator is like 1, you know?
Mm-hmm. So, the power.
2n plus 1.
Thank you. Yes, it's not a trick. It was not a trick question. It's once again, it's odd.
Right?
So if I put in 0 into 2n plus 1, it's going to start on odd. It's going to start on 1. Yeah? And then what else do I need? What else is this series doing?
Alternating.
It's alternating. So what am I going to put?
-1 and then to the n power.
Well, if I put it to the nth power, right, and I start it on 0, oh yeah, that works. Yep.
Wait, John, so when it doesn't start at 0, that's when we have to look out for what the alternator's power has to be to with n? Like n plus a number?
No, the alternator determines positive or negative, right?
Okay, yeah.
So you got to pay attention to the first term. In our case, the first term is positive. So we need to mess with the n so that the first term comes out positive.
Okay, so in what situation would it be like -1 to the n, like plus 1?
Right? That's
Yeah.
if the first term was negative in this case.
Okay, so it's either, is it just n or n plus 1, or could it be like n plus 3?
Pretty much, for the most part, yeah.
Okay.
And ooh, we forgot something. We forgot something, guys. Oh my gosh, how could you guys forgotten?
The 10. 10 to next.
What did we forget to do? What always comes out when you integrate?
Let's see.
All constant.
Yeah,
Plus,
guys, you left out that precious plus C. You brought me down to your levels. Oh,
Wow, John.
there's a.
Yeah, say it like that.
I'm sorry. I'm just kidding. I love you guys. Okay, so there's a plus C that comes out. So we kind of have to acknowledge it at least, right? We can't just ignore it. We can't just be like, okay, like it's not really there. If I close my eyes hard enough, right? It is there. It comes out. But there's something cool that happens. Look, if you look on the other side, well, I have an equation here with a bunch of x's, right? That means I can plug stuff in for x. So if I plug, let's say, an easy number like
0.
0, right? Why would I want to plug in 0?
Kind of cancel everything out.
So that all the x's go away. Like this goes away, this goes away, this goes away. The only thing left would be the c, right? So if I plug in 0, I can figure out what c is, right? So if I plug in 0, you actually end up getting tangent inverse of x is equal to, tangent inverse of 0 is equal to c. And what's tangent inverse of 0?
0.
Yeah. So c is actually 0 in this case. So you see how I had to cover my bases. You know, I had to make sure that c was 0, because if it was something else, the series would be something else. Does that make sense?
Yeah.
Okay. All right. Back to what we just found.
Wait, John. So in some cases, like when like the series would like technically go up to infinity, and then you have to add the c to it.
I mean, or you just bring the c to the front because addition is commutative, right? So
Well, like
order doesn't matter. So I could bring the c to the front if I wanted to.
yeah, okay. I don't know. It just seems kind of like weird because like you have like the whole like string of numbers and like plus c. No, like you really
Are you
don't.
happy?
You're
There, I
down
moved
down.
it for you. Gosh,
Thanks, John.
makes my job so much harder, man. All right. And look at that, guys. Look at what we just did. We just found another series representation of a function by using integration and differentiation. Isn't that crazy?
Yeah.
This is for also, once again, from -1 to 1. But what do we have to do?
We have to test
Test
the
the
endpoints.
Let's test the endpoints. This one specifically because one of them actually does work. All right, so watch. If I plug in -1, I get, and this is good practice for your quiz tomorrow too. So if I plug in -1, I get -1 to the 2n plus 1 over 2n plus 1. Okay, so let's simplify this and see what's going to happen here. All right, so -1 to the 2n plus 1. We have to kind of break this down and kind of like dissect it a little bit here. So this is the same thing as -1 to the 2n times -1 to the 1, I guess, right? -1 to the 2n. Well, I see -1 to the 2, isn't it? Right. So this is, let me do this off to the side here. -1 to the 2n is the same thing as -1 squared to the n by exponent rules, right?
Yeah.
So this is actually just going to turn into 1 because -1 squared is 1, and then 1 to the n doesn't really affect the series, right? It's 1 being multiplied to everything. So this whole thing is actually just going to go away, leaving me with -1 to the n plus 1 times 1 over 2n plus 1. You guys see that?
Yeah.
Because I still have to combine this one and this one. Do we see that or no?
Wait, John, why is it n plus 1 again?
So do you see what I circled?
Oh,
in blue?
because of that. Oh, yeah. I didn't realize.
Yeah,
that.
multiplying.
Yeah. Exponent rules. They follow you for life. All right. So what do we have here? We have an alternating, right? It's an alternating harmonic series, right? Because the bottom resembles like n. So you can say this converges by AST since, so this is decreasing and goes to 0. I'm doing really shorthands here just for the sake of time. But yeah, so at -1, this thing actually converges. We have to include -1 because it is a good representative of tangent inverse. So I'm just going to do that. And then we got to test what's going on at 1. So here we go. This becomes -1 to the n times 1 over 2n plus 1. What's going to happen?
It's going to diverge because harmonic.
Mm-mm.
Okay.
Anyone? Hello? Is anyone there? You guys listening?
Yeah.
What's going on this one?
Isn't this also?
Yes. This is also converging. Why?
Because it's harmonic, but it has alternator.
Exactly. Yes, it's the same thing as before. I don't know why
I thought it was a trick question.
I know. I've trained you guys to be suspicious of learning. Right? Good. Then I'm doing my job. That's
Yeah.
You got to question your learning, guys. Goodness, converges by AST also, because this is once again decreasing and goes to 0. So for this one, the interval of convergence includes both 1 and -1, and we see how this is actually different from, like 1 over 1 minus x, right? The first one that we did. So kind of going back to the point I was making before, yes, the radius of convergence will stay the same, but you still have to check the endpoints. How are we doing? Is this okay? Am I going too fast? Is this confusing at all yet? Or?
It's not that bad so far.
It's not that bad so far. Okay.
It's just like more steps.
Don't you
Yeah.
worry. Just you wait. It'll get worse. All right. So let's move on. There are, okay, I like to call them the 7 deadly series. Oh my gosh, why is it doing this? So I call it the 7 deadly series. But in reality, they are just, it's like commonly used. I'll define what this means in a second. Maclaurin series. Okay, so these 7 series are probably the most commonly used Maclaurin series in calc. All right, so I'm just gonna tell you what they are. I'm not gonna really go into like where all of them come from. We've actually we've come up with some of them already, and I don't have time to go into like to do all of them. I usually do, but it sucks. So here we go. So the first one was actually the geometric series. So I would maybe like make like a chart in your book. Make sure there's room for a chart in your book. So it's gonna go function. It's gonna go the summation, like the sum notation, and the interval of convergence, just like before. Let me move everything down. All right, so it's going to go function in summation notation, interval convergence. I'm not really going to require you to memorize these, but you will probably have to memorize them in the fall. So the function, the first one is this guy. And we just did this one, right? Summation notation, it's just x to the n from 0 to infinity. And then the interval convergence, I'm sure you're sick of it by now. It's 1 to -1. Second one is 1 over 1 plus x. And the only difference is this one has an alternator. And I hope that kind of makes sense. The third one is, you can guess it, tan inverse. And these don't really have like any particular order. I'm just writing them down as I remember them. So
The other one's gonna be just like trigonometry.
3 of them are trigonometry, yes. No, 2 of them are trigonometry. And we said this one converged on both endpoints. Can I scroll down, or are you guys still copying?
Going on.
You can scroll down.
I'll leave 3 up. The fourth one is ln of 1 plus x. Now, I'm not going to do this example with you guys, but I'll tell you how to get there. Ready? Well, ln of 1 plus x, what's the derivative of ln of 1 plus x?
1 over 1 plus x.
1 over 1
Yep.
plus x, which we have here already, don't we? So the
Yeah.
trick to get to ln of 1 over 1 plus x, I'm sorry, ln of 1 plus x is to just integrate. I'm sorry.
Right.
Yes, integrate 1 over 1 plus x. So you would integrate number 2 to get to number 4. Do you see what I'm saying? Yeah. So ln though, this one's kind of weird. There's a couple of definitions for it. I'm just gonna use this one. It goes n equals 1 to infinity. It's an alternator, but it goes n plus 1. And then I'm cheating, by the way. It's right, x to the n over n. Oh wait, and then the interval of convergence is, where is it? Oh yeah, it converges at the it converges only at 1. If you don't believe me, plug in the endpoints and check for yourself. So ln, I think, is probably one of the trickiest ones to do, or to prove. But yeah, if you have the time, honestly, try it. Start with number 2, integrate it, do term by term like we did with tan inverse, and then test the endpoints. Okay.
Yeah.
All right. Number 5, 6, and 7 are different. Okay. 5, 6, and 7 are gonna kind of be the reason for the second half of this lecture. So 5 is a sine of x. And this one is from 0 to infinity. It alternates, and it is x to the 2n plus 1 over 2n plus 1 factorial. And you guys notice, right? Sine of x doesn't look like 1 over 1 plus x or 1 over 1 minus x or arctan or whatever, right? So we have to use something else for these last three. So I'm going to show you after I give these to you. And oh, a really cool thing about these last three is the interval convergence. These actually converge everywhere, all three, the last three. Meaning the series representation is a perfect like example of the function for no matter what like x value. 6 is cosine of x. Looks like sine, except it's even. Once again, this also converges everywhere. Let me just double check. Yeah. Oh, sorry. These start positive. These start positive. My fault. And then the last one is E. This one does not have an alternator. It is just x to the n over n factorial. Yeah, these converges everywhere. These are the 7 deadly series. And the reason why they're called Maclaurin, okay? So here's the big reveal, okay? I know you guys probably think Maclaurin means like something super complicated because it sounds complicated, but it's not. Maclaurin just means, did you guys copy all this down? Can I move?
Yeah.
Maclaurin just means centered at x equals 0. That's all it means. It means that your interval of convergence, your center will always just be 0. And another way to kind of explain what a center is, you can think of it like a camera, right? What we're doing is we're looking at like snapshots of functions, if that makes sense, right? For the 1 over 1 minus x, remember when I showed you the graph? And like you saw that it only converged from like -1 to 1, right?
Yeah.
So that's what I mean. Like your picture is only in between -1 and 1, and your center is the center of that picture. Does that make sense? So Maclaurin series just means that you're always looking at 0, and like at some interval around 0. Okay. Yeah. That's it. That's what Maclaurin means. So we're still playing with series, power series. It's just we're looking at a very specific spot. All right. So where should we go? Okay, where should we go with this? So we need to know how to find like Maclaurin series. We need to know how to find the series representation, but now for any function at 0. Do we understand the task? Right? So like before we were like, okay, as long as it looks like 1 over 1 minus x, we're good, right? As long as it looks like 1 over 1 minus x, I can put it into this format and then like make it look like something to the n, like x to the n, right? And then go from there. But now the question is, well, sine, cosine, and e, and a lot more other functions out there in the world, they don't look like that. You can't manipulate them to look like that, right? So we need another tactic. We need another way for us to find the series representation for any function. Yes? Do we understand the idea here?
Yeah.
So we're gonna try this out. It gets a little confusing. Okay. Let me know if you guys get lost in the sauce here. All right. So I'll just title this, finding. I don't know, Maclaurin series representation for any function. All right, you guys ready?
Yeah.
Yeah.
All right, here we go. In the beginning, God created, no, I'm just kidding. In the beginning, right, I said that a function is represented as such. I think I might be switching the N's around, but whatever. Or the A's around, whatever. Right? In the beginning, this is what I said. This is a power series, right?
Yeah.
Well, if our center is 0, meaning if the picture is centered at 0, that means I can replace this A value with 0, right?
Yeah.
And that leaves me with whatever the sequence is, C sub n, times x to the n. So far, so good?
Yeah.
So all I did was the center is 0 because it's Maclaurin. Okay. If I string out the first, I don't know how much time we have. We have like 20 minutes left. So I'll string out the first like 5 terms. Okay, we'll go up to 5 terms. If I string out the first 5 terms, this is what I get. I get C sub 0, right? Meaning I plug 0 into the series, sequence, and then it spits out something. It's going to spit out a number, right? Times x to the 0, which is just 1. Plus C sub 1, x to the first power, plus C sub 2, x squared, plus C sub 3, x cubed, plus C sub 4, x4. I'll do that many. And once again, I'm assuming that this converges on some interval, right? Because that's how power series works. It will either converge on an interval, only at the center, or everywhere, right? So one day, a guy was just like, what's going to happen? What would happen if I just derived this like a bunch of times, right? These terms go off to infinity. So a guy was bored, they were probably going through a corona thing of their own at that time. And they were like, you know what? I'm just going to derive this thing and see what happens, right? So let's try that. Let's be bored and derive everything. We get, well, like I said, the C terms are technically constant terms, right? If I plug a number into a sequence, it's going to spit out a number, right? So I get that this first term, he's going to mute everyone. So the first term just goes away, right? Because it's a constant term. The next term is C1, because the derivative of x is just, 1. And then the next term after that is 2c2x. And then the one after that is 3c3 x squared. The one after that is 4c4 x to the 4th. And we saw that the first term got eliminated, right? Once again, let me know if I'm going too fast here. And that's the first derivative. Let's do the second derivative.
John, is that supposed to be x to the 3rd?
Yes.
4c4.
Yes. Good catch. All right, so now we're going to do the next derivative, okay? So we see that the C1 term goes away because it's a constant term, and you're left with 2C2 plus, I'm going to write it a very specific way. I'm not going to write it as 6, okay? I'm going to write it as 2 times 3, C3, and then 3 times 4, C4. You guys good so far? Let me know. Let me know if I'm going too fast. And then I'm going to do the third derivative. I'm going to do this until you guys see the pattern, because there's a pattern that starts to emerge. 2 times 3, C3. I forget the plus. Plus 2 times 3 times 4, C4x. Oh man, I should have went out to 5 to the fifth power. I'm gonna just tack it on at the end there. So it's gonna be plus C5x to the 5th. This one becomes 5c5x to the fourth. This one becomes plus 4 times 5c5x to the third. And this one becomes 3 times 4 times 5c5x squared. Oh no, I can't zoom out. It's not letting me zoom out. Okay. What do we think? Do we see anything?
Like the more you derive it, eventually you just cancel out all the terms.
Okay, yes. What if I plugged in like 0 in for everything? Like what would be left for like each one? So okay, fine. What if I did p of 0, right? What would be the term that's left over for the first guy? If I plugged in 0 for x, what would be left? Okay.
Just
silence here. I don't know why. If I plugged in 0 for all of these, all the way up until infinity, what would be left?
Just
First.
0. Wait, just the first one.
Just the first one.
Yeah,
C
just the constant.
C sub 0.
Oh, I know what this is.
So this becomes C sub 0. If I plugged in 0 into the first derivative, what's left?
First one.
Just the first term.
This goes away, this goes away, this goes away, this goes away to infinity, right? You're left with
C sub 1.
C sub 1. Okay, hold on. Second derivative, I plug in
C sub 2.
Hold on. Don't rush. Look at your notes. What's left?
2 C2.
2 sub 2.
Okay. 2
John,
times,
can I say it?
let me just show this one.
All right.
This is, you're left with
2 times 3 times C3.
2 times 3 C3. Go ahead, Harry. What do you see?
Isn't this sort of resembling telescoping series? How the
Not
terms in the middle
telescoping.
eliminate themselves and you're left with the first term?
No, this isn't telescoping series. Okay, maybe what if I did this?
Oh, so like
As the terms get bigger,
constants,
then it goes
like the constants outside.
like if you were to do the fourth one, would it just be
compare this? Tell me, what do you guys think the fourth derivative at 0 would look like?
1 times
1
3
times 2 times 3
times
times
3.
4 times c to the 4.
Yes.
So how would you?
How do I represent
Yeah, I don't
something
know.
to times, like, or 4 times 3 times 2 times 1?
Factorial?
Factorial.
Guys, there's a factorial happening here, and I guess I never forgot to say this.
Oh my God.
0 factorial is actually 1. There's a long proof for it in math, but that's just it's a thing you're supposed to know. But yeah, what we have here is a pattern of factorials happening, right? This is 2 factorial C2. This is 3 factorial C3. This is 4 factorial C4. This thing wants to load.
And factorial.
We see a pattern of factorials emerging here. Isn't that crazy, right? So, so what that means is if I were to go to P sub n, I want to make sure I say this right. The nth derivative at 0, meaning I have my function and I derive it in n amount of times, this is going to be n factorial C sub n. Thanks, Lamech. Thanks. I needed to see that. Thank you. What this means is we can start plugging in. So long as we know what function we're like investigating, we can plug in like the derivatives of that function, right? And then plug in 0, and whatever it spits out, we can figure out what the sequence is. We can figure out what the sequence is going to be. No, I feel like. Hold on.
Could you say that again?
If we derive the function enough times, right? There's going to be a pattern that starts to emerge. And when we figure out that pattern, I'm saying you can figure out what that sequence part is going to be, because this x to the n is just going to be, it's going to be x and then x squared, x cubed, that's just going to be like that forever. It's this part that we're trying to figure out here. Does that make sense?
Yeah.
Right. So watch. This is what we're going to do. I'm going to take sine of x. So now that we kind of have this guy, right? I'm going to rewrite it here because I'm like all over the place. I'm sorry, guys. So I have the nth derivative at 0 is n factorial c sub n, right?
Mm-hmm.
So if I just move this stuff around, if I just move some stuff around, and I do this move right here, do you guys see what I just did there?
Yeah.
I can solve for my sequence. My sequence is going to be the nth derivative at 0 over n factorial. So what we just figured out was the Maclaurin series formula for any given function. The Maclaurin series formula. This is a very important formula, right? So this means a function, right, is going to be closely resembled by its derivatives centered at 0 over n factorial times x to the n. How are we doing? Confused?
I understand.
I know it's a little confusing.
Definitely need an example.
Yeah.
Yeah.
I remember when I was learning Maclaurin and Taylor series, I was like, I have no idea what's going on. I don't know.
Wait,
That was
John, why is it
so
called
much writing.
Maclaurin?
Why is it called
The guy who
Maclaurin?
figured it out.
Centered at 0. This is because
No, like the actual name. Is that like
The
the
guy's name?
dude's
or-
name?
Oh, I don't
Yeah.
know. Sure. Why do we call limits limits? Why do we call L'Hopital? You know, they just wanted credit. I don't know.
I would do the same exact thing. It's like having kids in middle school and high school to be like Lamech.
Lamech's rule.
Like, oh. Yeah.
Okay.
Be like, yo, who's that guy? Yo, that's Lamech. Remember, he's in your textbook. Immortalized.
Whatever. You do it for the thirst for knowledge, right? You don't do it for the fame, man. That's how you can tell. That's how you can tell, you know. So this is what we're going to do. We're going to come up with the Maclaurin series representation of sine using this formula now. Sound good?
Yeah.
Yeah. So first part, you're going to have to derive this function a couple of times, more than a couple of times, actually. Okay. In this case, I'm going to derive it, I don't know, like 4 times. Let's say 5. So here we go. The derivative is cosine. The derivative of that is negative sine. The derivative of that is negative cosine. And come on. You can do it. Is it freezing on your screen too? Because it's like,
Yeah, it's like
yeah.
gosh.
There you go.
Okay. 4th derivative, and it goes back to sine. I'll do one more just in case. Okay. The next thing you want to do. Okay, so this is step 1, right? I know you guys like steps. This is step 1. Okay, so the next thing you want to do is plug in your center. Okay, so plug in center. And what's our center?
0.
0.
0, yes. So P of 0, well, what's sine of 0? Oh,
0.
please answer this correctly.
0.
Yes, it's 0. What's the derivative? The first derivative at 0 is cosine of 0.
1.
1.
Second derivative at 0.
0.
Third derivative at 0.
-1.
Fourth derivative at 0.
0.
Fifth derivative at 0.
1.
Okay, so we plugged in our center. And I don't know if I should show you the shortcut first or the long. I'll show you guys the long way first, okay? So next, you're gonna plug in these. These have a special name, by the way. These are called. You'll hear them. You'll hear the word this. You'll hear this being thrown around a lot.
Taylor.
You'll hear Taylor coefficients being thrown around a lot. Okay, so the third part I would say is plug into. I'm trying to think like how to do this. Plug into whatchamacallit. What did we say before? It was like.
With the formula thing?
No, not the formula. It was C sub n is equal to this thing, right?
Yeah, over n factorial.
Okay, so what do you, so this is going to be the part where you have to like think a little bit here, right? You're going to have to like think what pattern is going on with my Taylor coefficients and how can I plug it into this formula here? Do you guys notice anything that's going on with the Taylor coefficients?
It's like alternating between 1 and -1, and like
It's alternating, right, between 1 and -1, right? So if I I'm gonna write it out. If I write this out, this becomes oh no, I was supposed to be doing this. Sorry, it was the formula, right? So the sum from 0 to infinity. So if I write out the first couple of terms, right, I get, what is this? So the 0th derivative, which means, don't derive. Plug in 0 over 0 factorial x to the 0 plus the first derivative, plug in 0, 1 factorial x to the 1 plus the second derivative, 0, 2 factorial squared plus third derivative 3 factorial x cubed. I'll do one more. Come on, RAM. Oh my gosh, this thing is like, there we go. Okay, plus fourth derivative at 0, 4 factorial x to the 4th, plus so on and so forth. Okay, this thing's gonna go on forever and ever and ever. Well, we just figured out some of these, didn't we?
Yeah.
Yeah.
So let's start plugging them in and see what happens. So this guy, what did we say that was at 0? The
0.
original function.
Zero.
Sine of 0, right? And what that ends up doing is it actually cancels out the whole term, right? What was the next term?
1.
It was 1, right? So it was x over 1. What about the next one?
0 canceled out.
This one goes away. What about the next one?
it was
Negative
-1.
1.
Well, okay, so it was -1 over like 3 factorial times x cubed, right?
Yeah.
Okay. The fourth one was,
0.
this one also got canceled out. Do you guys see a pattern yet, or what? Do I have to spell it out for you? You guys can't. You guys don't see it? Can you guess what the next non-zero term is going to be?
Negative. Actually, wait, hold on.
1 over 6 factorial x to the 6th.
Nope.
Then no.
Could be 5. So would it be 1 over 5 factorial x to the 5th?
1 over 5 factorial x to the 5th. What would the next non-zero term be?
1 to
1 over 7.
1 over 7
Negative
factorial.
1
That's
over
odd.
6 factorial.
Do you see the pattern yet, or no?
They're odd.
Yeah.
Are odd
Oh, they're odd.
exponents happening? So if there's odd exponents happening, it's alternating. and then the denominators are odd factorials. And this is going to go on at forever. Meaning, I can rewrite this as, so what did I say? Alternating, x to the odd, and then all over odd factorials. This is what we wrote before for sine of x. This is sine of x.
It all comes full circle now.
It's supposed to, but I'm kind of getting the vibe that no one was really listening or caught that.
No, I understand.
I really hope you caught it, or I hope you guys like rewatch this video. You know, I hope that like me recording these lectures is just not going in vain or anything. So this third step, it's a little tricky. It's a little tricky, especially for this one. But it gets a little tricky because you have to identify the patterns that are going on in your series, and basically just write it out. Like, I know some people are like really stubborn or like prideful, and they're like, oh, I can figure out from the first like 2 terms. Like, no, you should definitely string it out to like the first 5 or so terms, meaning you're going to need the first 5 derivatives of your function, right? Plug it in and see what's going on. Try and pick up on the pattern that's going on. For this one, right, we had to go up all the way to the 7th degree, right? So if that's you, then, you know, that's fine. Just go out as many terms as you need until you start to see the pattern.
I have a question.
Yeah.
You said there was like a shortcut, like before you did all of this.
Yeah, I take that back. I don't want to show you guys the shorter way.
Bro.
Dang, I'm crazy.
I want you guys to understand this stuff, because like I said, when I was learning this stuff and I saw all this garb on the board, I was like, I have no idea what he's doing. I have no idea what this professor's doing. And then he started doing the shortcut way, and I'm like, what? I don't know, like, WTF, like what are you doing on the board, right? And I ended up just copying everything he did, and I didn't understand it, and I did not do well in Calc 2. So what I encourage you guys to do.
Could you at least do this shortcut at the end of EOF or something like that?
I mean, we only have 1 lecture left, man, and I gotta get through what I gotta get through.
No, like I'm not like after the final, like when
the
we
shortcut,
do the final
honestly,
class and everything.
The shortcut depends on how well you recognize patterns.
Mm-hmm.
Like when you do enough of these, right, you start to see like in step 2, there's like a pattern that starts to emerge. Like in step 2, I noticed that there was a pattern going on. Like I knew that there was an alternator happening and the even terms were going away.
So like the shortcut basically trying to skip the third step and then.
Yeah, like to skip all this plugging in stuff and just plugging in the nth, like this guy, which ends up being this. Because if I plug that in along with the fact that there's no even terms, you can get to here easily.
So it's less of a shortcut, more of a mental math thing.
Sort of, yeah. But I'd rather you guys like understand the long way.
Yeah.
And kind of truck through the long, harder way and then understand it, than just try and do this on your head, because it gets a little crazy. This is an easy, sine is an easy one. When you start doing like LNs and stuff like that, they get a little weirder, right? I encourage you guys, I know I'm going over time, I'm sorry. I encourage you guys to try cosine of x. Try coming up with cosine of x and e to the x. Okay, e to the x is really, really easy. Do you know why it's really easy?
Because e to the x
is just the derivative.
The derivative of e to the x is just going to stay the same, right? So I would try finding the Maclaurin series for e to the x and cosine x. Cosine x is going to look a lot like sine of x, except the odd terms are going to go away instead of the even terms. Okay, so try Maclaurin series for e to the x and cosine of x. Derive it a bunch of times, plug in the center, and try and find the pattern and use the formula. Once again, the formula is, I would definitely memorize this formula because it's very important. N factorial x to the n. Okay, it's a very, very important formula. All right. There was more I wanted to do today, unfortunately, but I guess I have to just push everything to Wednesday. your quiz tomorrow, don't worry, there's no Maclaurin series on it. Just make sure you know how to do power series and testing regular series. Oh my gosh, please don't find interval convergence for the regular series. I know some of you are going to do it. Please do not do the interval convergence thing for the regular series. Because like on the last quiz, I even told you guys, make sure you know the difference between sequences and series, but everyone treated the sequences like series. They started doing tests on the sequences questions, right? So once again, heed my warning. Do not do power series stuff on regular series, okay? You've been warned. If you want to stick around, ask me some questions, by all means do it, but if not, I'll see you guys on Wednesday for our last lecture. You guys are free to go.
John, this was lesson 10.7 that we just did, like this whole lecture? Or was it in addition to 10.6?
It was, okay, so it was 10.6, and then when I started talking about the Maclaurin series stuff,
10.7.
that was like going into 10.7.
Okay.
But the thing is, it's not, we didn't talk about Taylor stuff yet.
Yeah,
so
I know.
But Taylor's easy. Taylor, I'll just tell you now, the only difference between Taylor and Maclaurin is the center.
Oh, so it's the same process.
Exactly. It's the same exact process.
Okay.
It's just Taylor's problems usually take longer. That's because the center is not zero.
So if for Taylor, does that mean that the center is dependent upon what you're given?
Exactly. So for Taylor series, the only difference is that the center is not zero. It's some other number. So I could say that the center is at 4, or the center.
So then you would do
7.
P of 4, P prime of 4.
Exactly. The number you plug in is going to be the center, which is 4, or whatever. But we'll talk more. We'll do some more examples on Wednesday with Taylor.
One of these days, I'm gonna spend my time deriving some random thing, and maybe I can get something named after me after that.
Okay, Lamech. When that happens, let me know, please. I want to be the first person. You better tell me first out of everyone.
Yeah, I'll tell you to be right out. Like, yo, it worked out. It worked out. Like they had us locked down, but then I came up.
Oh my gosh, you can win a prize.
You'll get bragging rights. Be like, Lamech was my pupil.
Yeah.
John, if we have 2 hours for the final, how many questions are we gonna have?
I still have to make or tweak the final because, yeah, I'm still not sure at this point.
Okay.
Yeah.
Heard you.
But don't you worry, it will take you the full 2 hours. Don't you worry, Ollie. I would never deprive you.
I was hoping you wouldn't say that.
All right, John. Take care.
All right, see you, man.